far in the previous slide, I was breaking this bond or breaking that bond. Now we're going to break this bond here, okay? So in the previous slide, I showed basically breaking bonds heterolytically. Remember, alpha cleavage is almost always homolytic cleavage. So I'm going to break this bond basically by pushing an electron onto each atom. So one of the electrons goes on to form an ethyl radical, and the other one comes over here to form a new double bond onto this system here. So this is Mz equal to 87. I also have a choice of doing it in this fashion because now I have this other alpha cleavage. If I break that, I make methyl radical, and I make a new Mz of 101. If I do it in the other direction here, since this is symmetrical, I only have to show one, I can get an Mz of 101. So I have a lot of different ways of making 101, and I have 87. So if I go back, let's just remember 101 and 87. That's both of these. Okay? So they're not formed, and in this case, the alpha cleavage is not formed that well. The best one is 43. And the 43 peak, again, is being formed by breaking this polar covalent bond heterolytically, in which I make a secondary carbocation. Okay? Now I'll just mention one thing. I will not ask you 41. Okay? So again, if I had more time, if I had everything else, I would do this. But I just want you guys to recognize the following. The difference of 43 and 41 is what?
I see two.
It's basically 2, right? So you're absolutely right. To go from this and this, I usually do teach that mechanism, and I'm going to teach it to you guys. But you could think about taking 43 and somehow losing a molecule of hydrogen gas. So where do I see 43? Oops, going the wrong way. Here. If I somehow lost a molecule of hydrogen gas, I would basically get a allylic carbocation, where I form a double bond and a carbon with a positive. So going from 43 to 41, basically what I have is a double bond and a CH2 group here. And again, that's going to be more stable because it's resonance stabilized. Again, I'm not going to teach you guys that mechanism, but again, I wouldn't ask that on the exam. Okay, so again, I'm going to keep it very simple to McLafferty, alpha cleavage, beta cleavage, and then every once in a while, we'll see that we can break bonds heterolytically, particularly if they're polar. Okay, I'm not going to ask these other anything else. All right, just a couple final things here in these slides. Is up to this point, we've been really talking about low resolution mass spectrometry. So notice one of the things I was talking about was just adding systems. If I saw loss of a methyl group, I was just saying, okay, carbon's 12, hydrogen's 1, so 3 hydrogens, that's 3, plus 12, that's 15. So I was doing this using basically low resolution mass spectrometry. Okay, chemists today have access to this technique of determining really accurate molecular weights. And again, you could do this using higher resolution, which is called high resolution mass spectrometry. This permits you to determine mass molecular weights to 3 or 4 decimal points. Okay. Why? So again, I'll try to exemplify why one wants to do that. So, you know, all 3 of these compounds here have molecular weights of 32. However, if I use the exact masses of these atoms through high resolution systems, I can distinguish them. O2 would have a molecular mass of 31.9898. Hydrazine here would have a molecular weight, this should be an equal sign, apologize, of 32.03. And methanol here would have a molecular weight of 32.0262. So if I do high res, I could actually distinguish each one of these, okay? So, you know, sometimes you want to do that. You could think about, for example, you could think of drug labs, forensic labs, where you would want to have high-res systems to really determine molecular weights of systems that would distinguish one compound from another. So, you know, do you have this drug or something like that? It's also now used, chemists, organic chemists in particular, we're interested in high resolution. There was a time where we used to have to determine elemental analysis, and elemental analysis could be a pain in the rear. The compound has to be absolutely pure. In lieu of that today, when one publishes a paper in organic chemistry, you don't have to do elemental analysis. Instead, you just showcase a high resolution mass spectrum for the compound, okay, because of this resolution. So I just wanted to point that out. And so here are some of the exact masses of certain nucleotides that are found. And from this, you can determine, again, with that resolution, you can determine accurate molecular weights of compounds, particularly compounds that have roughly the same mass. Okay, so I just wanted to just show that to you guys. I'm going to finish off just sharing with you. We've been talking about electron impact ionization. This is chemical ionization. Really interesting. Here in chemical ionization, you don't use as much of a vacuum. So electron impact ionization, recall we used a high vacuum because we wanted to prevent molecules from colliding with each other to do bimolecular process. Here, we want the molecule to do some bimolecular processes. So we, instead of doing it at really, really low pressure, we do it at about 1 torr. So not as much of a vacuum. And what one does is often uses a carrier gas. Okay, so the carrier gases can be different. In this example, I'm showing methane here as a carrier gas. So we would take our compound, add methane to it, and we use a methane stream to push it through. What happens with methane here is methane will basically gets ionized to CH4 methyl radical. Okay, I'm sorry, CH4 radical cation. Okay, so where I lose an electron. Okay, now because I'm not using as strong of a vacuum here, I want methane, this species right here, to react with another molecule of methane. When it does that, it generates a species called CH5 plus methyl CH3 dot. Okay, so CH5 plus is interesting. At that point, it's highly unstable. At that point, that hydrogen is very labile. We'll transfer it to the molecule you're interested in, and basically you'll see your molecule become ionized through these chemical means and have an M plus H peak. Okay, so the important part with chemical ionization, it's a different technique where you're transferring a highly reactive molecule H to the molecule to generate M plus H. And so the important part to recognize is the molecular ion appears with a mass unit of 1 AMU higher. So if I had a mass of 98 of a molecular weight, if I do chemical ionization, it should have a mass of 99. Okay. So the other interesting part to this, and why one can see particularly difficult compounds that cannot be observed through electron impact ionization. This is chemical ionization. In general chemical ionization, the molecule does not have as much excess energy, and therefore fragmentation is often minimized. So compared to electron impact ionization that we just been spending time teaching you, this technique here leads to less fragmentation. Okay, so I just want to showcase, this is my last slide with you guys. This is the difference of MS of N-decanol. Okay, so here is the chemical ionization peak versus the electron impact ionization peak. Okay, so here you can see a very large peak here. Over here in 157, 141, I see nothing. Okay, so N-decanol using electron impact ionization, most of it fragments too fast to see the molecular mass of this. While using this technique of chemical ionization, I can see this, and the mass has 1 unit higher. Okay, so again, just want you to recognize there's distinct differences. If you can't see the molecular ion peak, then the thing that I just want you to be aware of is that you have the possibility of doing chemical ionization. The only point to recognize with chemical ionization, because it's transferring over a hydrogen, the mass, the molecular ion peak always appears with 1 unit mass higher. Okay, and that's it. That is it. And so It's 10:50 now. Just give me 1 second. Just want to show you something real fast. Where did I put it at? So, as I shared with you guys earlier today, after class, after office hours, I will post this up and permit you guys to talk to me either tomorrow about this and as well as Thursday. One of two things. So again, I should be able to finish polymer chemistry tomorrow. Okay, so what that means is Wednesday, I will use Wednesday to answer any questions with you guys. Okay, now I have office hours right afterwards, after today, which will take a few minute break. We'll start at 11:05. But one thing that I want to share with you guys is that I'm also going to offer office hours tomorrow. Okay, and the reason for this is I just want to give you guys more opportunities to ask me, and most of the meat of the material for the exam is going to be on chapters 22 through 24. Okay. Now I will have some mass spec. You'll see that the polymer chemistry will be very easy. What I'm going to test you on, it's not going to be weighted very heavily. So really at this point, I want to say that a significant portion of the exam, if not more than 80 to 85%, has been covered already. Okay. So I want you guys to start working really hard to reveal all the material that we talked about last week and Dr. Schwan taught you, and then really up to this point, the mass spec of today. The polymer chemistry is going to be very, very little. It's not going to be that significant. So with that being said, that's one reason why I'm not having a quiz on Wednesday. And instead, Wednesday, I do have office hours, but what I want to do is use my time from 9 to basically 11 with you guys to do that. If people are asking questions, I'll stay on. Otherwise, if you find that all your questions have been answered, then I really ask you guys to start studying. With regards to tomorrow, again, I will stay on just in case you guys have questions about this problem set or anything else with me. Because again, I want you guys to really use Tuesday as your last day to hone in and really study. Wednesday, ask me final questions and then really get prepared for the last exam. Now, I haven't started writing the exam. I started doing stuff, but what I want to do is I want to talk to Dr. Schwan because I want to just make sure how I've tested students in the past during a regular semester, I think it might be a little too hard. So I'm looking at problems in which I can make it not as difficult for you guys because, again, the chemistry of enolates can be challenging. And again, I'm going to try to tighten up the stuff I have. I probably have about 30 questions I could ask you guys. Okay, so I want to talk to them. There will be a multiple choice section. And the reason I'm thinking more about a multiple choice section is, to be honest with you, the answer's in front of you. So there could be a lot of predictive products, but so if I asked you guys to predict the products, you would have to come up with it. If I had a rigid section, will it be easier for you guys to recognize the right answer using A, B, C, D, and E? And I think there is benefit to that. Obviously, when I do predict the products, there's no partial credit. It's either right or wrong. So it doesn't matter if I give it an original section or a multiple choice section. Tomorrow, I will try to give you guys some more additional problems once I finish writing the exam. Like I said, I have a plethora of problems, but again, I don't want to give you guys anything until I decide what the test looks like. And I'll give you guys some additional problems that we could talk about on Wednesday. Okay, so with this problem set here, like I said, I'll post it with you. Very similar process here. Again, I probably will, I apologize, I wanted to give it to you guys, and this is from an old problem set I used. Please let me go through it this afternoon. I'll try to work it out before I leave today, because I believe there's some here that I don't want you guys to be to actually do. Okay, so specifically, if there's something on this one that I don't want you to go do, I'll send an email saying, please don't do. For example, I don't think you'll do 41. But again, I haven't done this in a while, so let me look at it. Here is another one that was taken from a different problem set that I had. Again, you can see the same type of thing. And then, as I pointed out to you, this was a question that Dr. Schwann had given me. Again, the points don't mean anything, but he had given it to me. Sometimes in multiple choice sections, and I'm not going to do this, sometimes it shows up which compound would show a molecular ion peak at 86 and a major fragment at MZ43. So you really have to think about these systems here. Again, I'll help you work that out. But again, if you could do these problems up here, you should be able to do this one. So it's a short problem set, but again, it just gives you more practice on the types of questions I'll ask you on Thursday. Is that fair?
Yep.